Let's move on to Lesson 11.6. We're now going to apply some of the things we just learned about triangles to circles. Theorem 11.6.1. If two chords intersect in the interior of a circle, then the product of the length of the segments of one chord is equal to the products of the length of the segments of the other chords. So, we have two chords that intersect inside of a circle. The product of the lengths of the segments of one chord. So we have a chord splitting through the circle, and it has a segment Y and Z. So the product is their multiplication. So YZ will equal WX. Or you can say that WX will equal YZ. In Chapter 8, we studied the measures of angles formed by secants and tangents of circles. Another way to solve the measures in parts of circles is to use these proportions that we've been learning since the beginning of Chapter 11. The relationships are basic to trigonometry. So even though they're not set to be fractions that are equal to each other, these are still proportions. So once again, W times X will equal Y times Z. Let's take a look at the proof that they have in your text. This is the same type of situation we had in the last circle. You can see that they've drawn lines to form triangles, and this is how we're going to prove that the segments of the chords are equal to each other. So they state, first of all, that circle O has a chord AC and a chord BD, and they intersect at E. Then we're going to draw lines AD and lines BC. We can do that because of the line postulate. And now we have angles. Angle A is congruent to angle B. And angle D is congruent to angle C. And this is because inscribed angles intercepting the same arc are congruent. So if you take a look at these angles that they formed, they both intercept arc AB. And we can also state that the triangle AED is congruent to the triangle BEC because inscribed angles intercept, because of AA similarity postulate. We know that we have the congruent angles. We know that we have vertical angles, and that's enough. We can now use a proportion similar to what we've used in the past, and we can say DE is to EC, as AE is to EB. Now what you should probably do on a piece of paper is make a circle and go ahead and mark these in color. The reality is there are other proportions you could have made out of this, but we want to prove certain lines so that we can state our last step. So DE, and they're looking at the similar triangles, will be corresponding to EC, and AE will correspond to EB. And that's because of CSSTP. And now we can pick the pieces that we've just set in proportion and multiply across. And we have DB times EB, so DB times EB equals AE times EC, which is our theorem. And we did that by using cross multiplication, or what they call the cross product property. So let's take a look at example 1. I split it into 2 parts. Find each measure, and A asks us to find this piece CD and AC. So knowing that we can multiply these pieces of the chords together, we can multiply 9 times x plus 10, and we know that that will equal the 2 pieces of the other chord, 24 times x. We use our distributive property, and 9 times x is 9x, 9 times 10 is 90, and now we will go ahead and subtract 9x from both sides, and we'll end up with 90 equals 15x, and x equals 6. So for CD, x equals 6, and now if we place the 6 into the x for AC, AC will equal 6 plus 10, which is 16. So you look at the product of the lengths of the first chord, and you set it equal to the product of the lengths of the second chord. So once again, the 9 times x plus 10, and then the 24 times x. Then you solve the equation for x, and then you state each missing measure. And we'll go to example 1b, and they ask us to find the whole segment QT. So we'll go ahead and we'll set our chords, the product of our chords, equal to each other, and that will be 2x times x plus 4 equals 8 times 3. So here it is in our equation. 2x times x plus 4 equals 8 times 3. 2x times x is 2x squared. 2x plus 4 is 8x equals 24. If we divide both sides by 2, we end up with x squared plus 4x equals 12. And whenever you see this form, you should be able to recognize that this is a quadratic equation. So we take this whole equation here, and we subtract the 12 from both sides, and set the equation to 0. From this point, we find factors, and we're looking for the factors of 12 that will add to positive 4. So, the factors of 12 that will add to positive 4, or will become positive 4, would be 6 and negative 2. Positive 6 and negative 2 equal 4. And we go ahead and we set each x to 0. So x plus 6 equals 0, which means x would be negative 6. X minus 2 equals 0, which would be x equals 2. And we'll use the positive answer to this question and substitute it in our equations. Now, we were to solve for QT. QT is this whole line. So QT, actually, you don't actually have to do this step, but QT equals QR plus RT. So we go ahead and substitute, and the QR was x plus 4, so 2 plus 4, plus, and RT was 2 times x, so that's 2 times 2, and the total will be 10. Your homework is numbers 1 through 3, 6, 7, 9 through 12, and what I've done is I've given you the answer starting with number 2. So when you go to solve, you have to show me your steps, and your answer should be the same. If you have difficulty, contact me. Number 1 I didn't do because number 1 is actually having you restate our theorems. So have a good day, and contact me if you need me.